Alright, I want to consider the potential energy in a capacitor. This would be a plate with opposite charges, and I think the most logical way to go about that is to build up the energy and look at how much work you do to create that energetic situation between these two plates. And rather analogously to how we consider gravitational potential energy. How much work do you do to create the energized situation comes from the separation, and what you would do is grab a little mass and pull it through the gravitational field away from the Earth, so to increase the separation, and you look at how much work you do. Now if you're close to the Earth's surface, then the gravitational field is fairly constant. The mass which you take away from the Earth does not change the Earth's mass, and so the gravitational field would stay fairly constant, and you would look at the mass moving through the gravitational field and the distance that you move it to get the amount of work that you did. Of course, if you moved it far from the Earth and the gravitational field became significantly weaker, then we would have to do an integral. But the important difference between here and the electrical case is that we do not change the Earth's mass when we pull mass away from it and pull it up into the sky. But in this case, if I grab a charge, say an electron, and move it up to the top plate, I'm going to be moving that charge through a field, and so there will be a force as charge is acted on by the field, and we could look at the distance through which I move to get the amount of work that we do. But the difference here is that in pulling charge out of this plate and up to the top plate, I'm also changing the field, whereas the gravitational field was not changed by my ripping mass loose from the Earth. The electrical field is changed as I pull more and more charge out of the bottom plate and put more and more onto the top plate. The field is going to respond to that, and so it becomes a little bit trickier situation. We cannot do an integral of the charge times the field strength, and that would be the force and the distance through which it moves. This will not work. Get rid of that. That instead what we're going to do is to think of little infinitesimals of work that we do by looking at the definition of voltage was work per charge moved, and so we have this expression that it would be the voltage, the potential difference between the two plates, times the amount of charge moved. Instead of the distance that I move it, I'm going to look at the amount of charge. And this is missing a bar here. We'll put it in. What color are we? Black. Okay. I don't know why that doesn't work better, but that V in the case of a capacitor, these two locations, would be equal to the charge divided by the capacitance. That is Q CV. So I'm going to use that to get the amount of electrical energy that I do. It's the electrical potential energy here in this capacitor is going to be equal to the negative of the work that I do from the work kinetic energy theorem, and the work is going to be adding up all the little infinitesimals of work. So we put this value in here. Notice the negatives go, and you have this. And if you evaluate this, here you have a function of Q and you're integrating it dq, you do get a Q to the second, and then a 1/2 comes out front. So here's an expression for the electrical potential energy in a capacitor. It depends upon the charge on the capacitor and the capacitance of the capacitor. This is a formula to be memorized. Now I have a mnemonic for this. I take the 2C and I multiply it times the u, so that I have 2cu equals q squared, which one can read as 2q equals q2. And that works for me. I can remember the formula. Of course, you can take this formula here, and you can replace the q by CV. And so you get a c squared v squared on the top, and that together with that c gets you this alternative. This is also an expression for the potential energy in a capacitor. This time the capacitance and the voltage as opposed to the charge and the capacitance. And you can replace V by Q over C. No, that would be this one. I can replace C by Q over V, and you have this alternative expression for the potential energy of a capacitor. All three of these will be things that you will use from time to time. I always go back to this one, and also to AQCV. And I build my way to these every time I need them. But you could memorize all three if it gave you pleasure. So, consider these two capacitors of the same area, but differing separations, D1 and D2. And recall that the amount of capacitance depended on the geometry only. So for parallel plate capacitors, that having the same area should lend to them having the same capacitance, but having a greater distance between them, yes, capacitance was equal to epsilon A over D in the case of a, that shouldn't be there, in the case of a parallel plate capacitor. I should have gotten you to come up with that, but there it was. My show was messed up. It was already there. So, but D2, this distance perhaps is twice this distance, so I can replace D1 by 2D2, which is 1/2 of epsilon A over D2, which is the capacitance of capacitor 2. So to have twice the distance is to have half the capacitance. We could have just looked at this formula here and seen that. But I also want to consider the energy. And recall that energy is stored in the field of a capacitor. And so if we look at the potential energy here, then we pull in this thing, and here I'm going to go with Q2 is equal to 2Q, except I've rewritten it this way. So the potential energy of this capacitor here would be equal to this quantity, but then I can replace C1 by 1/2 C2, which I got there, and so this ends up being equal to Q squared, same charge here, Q squared over C2, which is twice the potential energy. 1/2 Q squared over C2 would be equal to the potential energy of this one, and so we see that this one, if it is the same charge on these two and the same area, this one with twice the distance would have twice the potential energy. And perhaps you would like to convince yourself that the field would not be affected by that pulling apart, and all you need to do is make yourself a nice Gaussian surface, that these two plates have the same charge and so the same surface charge density, and so the field here, if you did the Gaussian treatment of it, this being a conductor, the field would, oh boy, and I hope I get this right, is equal to the surface charge density over epsilon naught. If it was an insulator, then it would be over 2 epsilon naught. But for a conductor, it was over epsilon naught. So there you go. At any rate, it would not matter how far apart the plates were, that the field inside would be the same if there were the same surface charge densities for those two. This is probably something I should have mentioned another time, but we fit it in here because I didn't remember it when I was doing earlier lectures. But what do you do when you have a parallel plate capacitor but the plates don't line up? And in that case, what I would suggest is, let's go with yellow, that you think of this arrangement as 3 capacitors in parallel with one another. But this one, missing the opposite plate, has no capacitance. There is no area for this one when you do the parallel plate capacitor. Of course, there's the isolated capacitor situation, but I don't want to talk about that. So the capacitance, let's get a color we can see, the capacitance for parallel plate capacitors being equal to epsilon A over D. I guess the effective A here is 0, or the effective D here is infinite. At any rate, there's no capacitance here and here. And so the result would be, when you add these 3 capacitors up in series, that you only have this capacitance here. The point, which I could have said without all of this blather, is that only the overlapping parts contribute to the capacitance of the capacitor. So that's dealing with A in this kind of awkward situation. What do you do with D varying? What would you do if you had a parallel plate capacitor but they weren't parallel plates? And what I would suggest in that instance is that you cut up that parallel plate into a bunch of little infinitesimal plates which are parallel to this. All of these capacitors would be in parallel with one another, and then you could do a continuous summation of all those capacitances for those parallel capacitors. So we won't bother to go through it, but you could deal with parallel plate capacitors where the plates are not parallel. Okay, want to go on and talk about what happens when you put something between the plates of any capacitor, cylindrical, spherical, parallel plate, or irregular. I don't think there is such a thing, but suppose there is. Suppose you put something into this space. Molecules. Because there is a field here, they will tend to have local charge induced in them. And so the effect of that is going to induce local charge, but then once they get that local charge induced, they will tend to line up with the field, like this. But when they line up with the field, that creates a field which goes in the direction a positive would go, which is contrary. Put them up here. Contrary to the field that induced them. And so once again we have this situation where the result of something being in there is that the field will cause it to line up, which will create a contrary field, which will indeed weaken all of these messages were sitting here, will weaken the field between the two plates. This material that you put in here is called the dielectric. And you'll see that word on the next slide. I mentioned that this fluid that goes in here must be non-ionic. And I would like you to complete this. What would be, suppose you put salt water in between here, in between the two plates. How would such a capacitor behave? What would happen? What bad thing would happen? The other thing that I wanted to do was that so this is a point already made, that for some materials they will polarize more readily, line up, make a stronger field opposing because they line up so well. So the better induced polarization is going to make for a weaker field, and a weaker field, of course, is going to mean less energy is stored between the two. Or if for a given charge, or the other effect is that you move through the field through this distance. If distance did not change, and you have this expression that V is equal to the negative of the integral of E dot ds, then if ds, the distance between these two, has not changed, and the field has gotten weaker, then it's going to necessarily mean that the potential difference between these two would get weaker when you introduce a dipole. We'll talk about that more. The material that you put between is called the dielectric. There it is. And we have a value called the dielectric constant, which is a property of the material, indicating how readily the material becomes locally charged and hence lines up, causing a weakened field. Here is a table from your book that you will need to refer to do homework problems, but it gives the dielectrics of various materials. This, how readily it becomes locally charged and lines up. Air has a very small dielectric constant. It is the smallest. The only thing smaller than air is the vacuum, which has a dielectric constant of 1. But these other materials have increasing dielectric constants, which means they line up. They become locally polarized much more readily, and then they weaken the field accordingly, which is not necessarily a bad thing. We will show that you can get good things, that working with strontium titanate in between the plates of your parallel capacitor would actually make for a very good capacitor with a lot of capacitance, ability to hold charge. I was struck for the first time by these two entries here in the table. I would assume that this would have to be deionized water, because after all, if it was an ionic fluid, and water typically is very ionic, which is why it's such a good solvent, you would think that it would do that bad thing that you indicated happened when you had a ionic fluid in between the plates of a parallel plate capacitor. So there is this value, the dielectric constant. Oh, before we go on to this, notice this table here, which is the word I was searching for earlier, and I think I called it the breakdown voltage. What I should have called it in the previous lecture was the dielectric strength, and its units are kilovolts per millimeter. And what that is indicating is how many millimeters of this material, for 1 millimeter, how many kilovolts of potential difference would there have to be before the dielectric gets ripped apart? It is no longer polar and becomes ionic, gets ripped apart into ions, and that's when a spark jumps. And it was using this value that I came up with the statement last year that if we were getting sparks to jump from the Van de Graaff generator a distance of 1 centimeter, that is 10 millimeters, then the potential difference between your finger and the bulb of the Van de Graaff generator must have been 30,000 volts. And that's how I came up with what the potential was on the Van de Graaff generator if it was throwing sparks that far. and you can throw sparks much longer than that, hence the statement that the Van de Graaff generator can hold as much as 100,000 volts, which would be evidenced by the fact if you could throw a spark 3 centimeters with 100,000 volts would be sufficient to cause air to break down and get that spark to jump. You can see the polystyrene is going to do a much better job of not breaking down and throwing a spark. Alright, back over here. So you have these values for kappa, the dielectric constant, and what you do with them is you take the epsilon in all of your equations. Here's the equation for parallel plate capacitor, but you also have an equation for a cylindrical capacitor and for a spherical capacitor and the isolated capacitor, and you just take that epsilon and replace it by kappa epsilon. So putting a dielectric in does in fact increase the capacitance of a capacitor. That after all, the capacitance goes up with the dielectric if you have the same charge on the object. Then it must have been that the voltage had gone down in order to produce that. So for a smaller potential difference, you can hold more charge if you've got higher capacitance. Or if you like, if we were to keep the voltage constant and you increased the dielectric, made the capacitance bigger, then you could hold more charge. You would have more capacity for holding charge, hence more capacitance with the introduction of a dielectric. Exactly the ideas I was talking about in the last slide are replicated here, that we have a circuit which consists of a capacitor and a seat of EMF. That B is for battery, although it looks like one cell to me. If you were to then stick a dielectric in between those plates, thus reducing the field strength but increasing the capacitance, that the capacitance having grown greater while the potential stays constant because of this seat of EMF, what that's going to mean is more charge. That what's going to happen is when you put the dielectric in here, this is going to pull more electrons off of this plate and deposit more electrons on that plate, increasing the Q when you put the dielectric in, increasing the capacitance. In this circuit, you have a meter which records the voltage, but it's not a pump. It's not a seat of EMF that's sitting here. So this time you have constant charge. There's no source, nothing to pump additional charge into the circuit. And so when you put a dielectric in this time, making the capacitance greater, if the charge is staying constant, then it must be that the voltage has gotten smaller. That's the only way you could have C be bigger if Q was constant, is V got smaller. And that's what this meter shows. If you consider the field here, the distance, the integral ds, is the same, but the field has been made weaker. And so we are not at all surprised to find that the voltage goes down when you insert the dielectric. In this case here, again, the field would tend to get weaker because you put the dielectric in, which would tend to make the voltage smaller, except this thing says no, the voltage is staying the same. And so what happens is this additional charge goes onto here to augment the field. Introducing the dielectric decreases the field, but increasing the charge increases the field back to where it was, so that the voltage stays the same. Finally, this is a little prep for your homework problems. In the book, these colors are much more delicious looking, like sherbet ice cream sandwiched between the plates of a parallel plate capacitor. But they're going to ask you to deal with, you put different dielectrics in here, and what is the capacitance as a result of that. And I hope it's obvious to you that what you have are two capacitors in parallel. That is, there would be the same voltage drop across both of them. And so you would just use that dielectric to get the capacitance of this one. Notice the area would be cut in half, and you could do that problem. What about when you have them like this? And when you put them together like this, what you ought to think about doing is taking a sheet of aluminum foil of 0 thickness and putting it right there between the delicious flavored layers. So this would do nothing to the total distance. You would have part of the distance here and part of the distance here, but that aluminum foil would take up no distance. But then you would have two capacitors in series, and so you could find the equivalent capacitance for doing that for those two. Of course, if you were to insert this big piece of aluminum foil that was very thick, then we would need to take into account the fact that sticking that in there has decreased the effective distance between the plates, because here there is a capacitor with zero capacitance between the top and the bottom of a conductor. So you would have to, and look at what a wonderful challenge that problem will be. Thank you very much.